The common ion effect is used sometimes to explain how to get rid of one particular bad ion, if you will. And in the process of getting rid of the bad ion, you end up adding something else, and we'll talk about that here in a little bit. But in this picture down here on the bottom, we're talking about silver acetate. Silver acetate is somewhat insoluble. You can see in the little test tubes there that there's the white solid on the bottom, and that's silver acetate. But there is more acetate in the solution over the solid, and we'd like to get rid of it. So what we're going to do here is we're going to add silver nitrate to the solution. So we're adding silver. Silver is an ion common to the equilibrium that we're studying. And as you add silver ion, silver reacts with acetate even more, pushing it to the reactant side, which in this case is insoluble silver acetate. So you can see in the right-hand picture there's even more silver acetate in solution. On the far right picture, you can see there's only one little red acetate above the solid. So that's trying to show that there's less free acetate than there was before. However, by adding an ion like this, we're adding in another species. So we're adding nitrate from silver nitrate. So at the end now, nitrate is running around. It kind of takes the place, if you will, of the acetates that formed a solid. And that's another consideration to realize. You can't have something for nothing usually. We're adding silver nitrate. A lot of the acetates go into the solid, but we do end up then with nitrate in the solution, which can be a problem or it can be something cool. Depends on what you need to do.
In the test tube is a solution containing lead ions. To this we add a solution containing chloride ions and lead chloride precipitates. Solid lead chloride is in equilibrium with lead ions and chloride ions in solution. At this point, we add more chloride ions in the form of a sodium chloride solution, which disturbs the equilibrium. More lead chloride precipitates, which removes still more lead ions from solution.
This video shows what happens when you have lead 2+ and you want to get it out of solution. You want to precipitate it out as PbCl2, lead 2 chloride. All right. So in the far left-hand column there, both in the top and the bottom, you can see there's a yellow line for the lead 2+ concentration. That's how much lead 2+ is in solution. And we have on the top no green PbCl2. But the first red dashed line, that's when we're adding some chloride. It's probably sodium chloride or something like that. We're not usually too concerned about the counter ion, but it is something to consider. But anyway, adding the chloride then, the chloride begins to act with the lead 2+ to make PbCl2. So on the top graph, a first little green line appears. It kind of maxes out after a while. That's because the lead and the chloride are reacting to make a solid. So in the lower graph then, you can see chloride starts kind of high and goes down because a lot of the chloride is used to make the green line above the PbCl2. But most importantly, our lead 2+ concentration does go down, but it doesn't go down perhaps as much as we'd like. So the second red dashed line, we're going to add another chloride addition. Again, another source of sodium chloride or whatever. And you can see in the top part there, the green line gets even higher. That's because we're making more PbCl2. And in the bottom down there, you can see how the lead 2+ concentration is certainly decreased. All right, it's gone down a lot. It's not zero like we talked about. Hopefully this is a level we're happy with, but it is something to be considered. You never totally get rid of these things, but you can wipe them out by several orders of magnitude. So this is the common ion effect. You're probably adding sodium chloride to make the PbCl2 crash out, make it precipitate, and in the process then you are left with chloride and then some kind of counter ion, for example, sodium and sodium chloride. So let's calculate the solubility of barium sulfate in pure water and in the presence of some barium ion. Now, barium nitrate is a compound that's very soluble in water. All nitrates are soluble. It'll break down into barium 2+ and nitrates. It's the barium 2+ we're going to be interested here in B. So for the first part, KSP equals 1.1 times 10 to the minus 10 for this reaction. And notice that KSP equals barium times sulfate. All right. So So in pure water, we're just going to calculate the solubility. Solubility will equal the barium 2 plus. It'll also equal the sulfate. So what we'll do is we'll let X equals the barium ion concentration and the sulfate ion concentration. So KSP equals X times X or X squared. We'll solve for X and we're good to go. But for the second part, we're going to have some barium already present. Now, think back to Le Chatelier's principle. If you were to add a product like the barium 2 plus ion, by Le Chatelier's principle, that should make this reaction go to the reactant side, i.e. shift to the left. And what that's going to do is that's going to lower the solubility of the barium sulfate. Because if you start adding barium, there's like too much barium. The barium will react to a point with sulfate and make more barium sulfate, but the solubility will go down. So when we do the barium ion, we expect the solubility to be less than what it was in pure water. So let's check this out. So we're going to first look at A, which is just the pure water example. The solubility equals X, which equals both the barium ion concentration and the sulfate. So it's like KSP equals X times X or X squared. And if you want to solve for the solubility, which is what X is, square root of KSP, 1.0 times 10 to the minus 5. So in a liter of water, you can dissolve 1.0 times 10 to the minus 5 moles. That's in pure water. Now in part B, we're going to have some barium ion already present. And again, by Le Chatelier's, you start adding the barium ion in, that's going to shift the reaction to the reactant side. Solubility, which is what we're measuring, should be less, all right? The barium is going to make the solubility go down. So we can test this out and see. Now we expect, like I said, the solubility to go down, all right? Adding an ion common to the reaction, i.e. the barium nitrate is adding a barium ion. That should make the reaction take a left, i.e. shift to the reactant side. That's what old Le Chatelier's principle would say. So we expect then in the presence of the barium ion, the solubility should be less. So let's check this out. Same KSP equals barium times sulfate, etc., etc. But the difference now, if you want to set up a full ice table, is that we have some barium already present, 0.010. Now, solubility has to be a positive number, and solubility will be the same as the sulfate. So I used a Y here instead of an X, but you could use X if you want to. So notice that at equilibrium, you'll have the barium plus some amount Y, and sulfate will be just Y. So if you use those equilibrium values and you set it equal to the KSP, which is 1.1 times 10 to the minus 10, you can solve for the solubility Y. Now, as default, this would be a quadratic formula. You'd have y squared plus 0.010y minus KSP equals 0, and you can go crazy. But however, in the last example, the solubility was pretty small, 1.0 times 10 to the minus 5. And we just predicted that in the presence of barium, the solubility y should be an even smaller number. So probably it is quite all right by sig figs to ignore the plus y for barium. So barium will end up being just 0.010. You don't need to worry about that plus y. It's going to be incredibly small. Remember with sig figs, when you add and subtract, it's always about the doubtful digit. So 0.010, that last zero is at the thousandths place. And 1.0 times 10 to the minus 5 has a lot more zeros in it. It's not even going to affect the small amount that it's going to create. So, make a long story short, ignore the plus y. So it's going to end up being just 0.010 for barium, still have the y for sulfate, that's with the solubility, and when you solve for it, 1.1 times 10 to the minus 8. That's the solubility in the presence of the barium ion. Now again, it was 1.0 times 10 to the minus 5. Now it's 1.1 times 10 to the minus 8th. So solubility has certainly decreased. It went from 10 to the minus 5 to 10 to the minus 8th in the presence of the barium ion. So this is another example of how Le Chatelier's principle can still help us out. It's a real powerful tool. It's helping us to figure out the directions of the solubility, helps us make sense of our answers and stuff. Le Chatelier's is pretty awesome.